Hello everyone, I'm David and I'm the developer behind the PySHRED package. PySHRED is a Python package for shallow recurrent decoders. And in this video, I want to introduce to you the features of the PySHRED package and walk you through a tutorial using the PySHRED package. So here's a quick recap on what we've seen so far. We've seen a vanilla version of SHRED where we map stationary sensor trajectories to the full state space. We've seen mobile SHRED where we swap out the stationary sensors with mobile sensors. We've seen SHRED reduced order modeling where we first compress the full state space using singular value decomposition and then fit SHRED on the compressed data. We've seen SINDY SHRED and Koopman SHRED, which are SHRED variants that perform exceptionally well at long-term predictions. We've seen transformer and UNET SHRED. So this is a variation in the SHRED architecture. The traditional SHRED architecture uses a long short-term memory network followed by a shallow decoder network. So here we're just using a transformer instead of a LSTM and a UNET instead of a SDN. In this video, I will briefly talk about multi-field SHRED, and in a future video, we'll talk more about parametric SHRED. All of these functionalities I've listed will be inside the PySHRED package. So the goal of PySHRED is to make SHRED as easy to use as possible and have as much powerful functionalities as possible. Here is an overview of what will be covered in this video. First, I'll talk about getting started. So this is installing the PySHRED package and importing it. Next, I'll talk about sensor and data processing. This is where you load in your high-dimensional data sets and select your sensor locations. Next, I'll talk about dataset splitting. This is where you do the train validation test split. And then I'll talk about how to fit SHRED on the dataset that you've split. And then I'll show how to evaluate SHRED once it's been fitted. And then I'll talk about how SHRED can be used on tasks such as reconstruction, prediction, and forecasting. And I'll also talk about post-processing, which is how we post-process the model output and uncompress, unscale it back to what it originally was. And lastly, I'll walk you through a tutorial of using PySHRED on sea surface temperature data. So getting started, the first step is installing PySHRED. Currently, PySHRED is only available locally, but it will be we will have its official release in a few months from posting this video. By then, you will be able to pip install PySHRED as it will be on the Python packaging index. Now, if you're eager to get started, you can install a pre-release version of PySHRED directly from the source, so you can clone our GitHub and install the package locally. And just a note, this is a pre-release, and this video also covers this pre-release version. So once the actual version is released, make sure you fall back on the documentation for the released version, as there might be slight differences between that and this video. So the first step, once you've installed PySHRED, is to import it. So simply you can run import PySHRED, and from PySHRED import *. So this imports all the attributes of PySHRED. The next step is sensor and data processing. So this step is where you prepare the data before SHRED is able to fit on it. The key component here is called the SHRED Data Manager. This is the manager that manages all your data sets and sensor locations. So let's take a look at the parameters in the code chunk here, where we're doing an example initialization of the SHRED Data Manager. here what we can see is we have lags, which is set to 20. So this means at each time step, we're looking back 20 sensor measurements to reconstruct the current full state space. We also have train size, which is the ratio of the data set that we want to train on. Val size is the ratio we want for validation set. Test size is the ratio we want for the test set. And then compression is the number of components we want to keep when we run singular value decomposition. And lastly, we have mode. And with mode, there are 4 options. There's reconstruct, predict, forecast, and all. And I will talk more about this. One of the parameters we've talked about in the SHRED Data Manager initialization is lags. So lags is the number of time steps we want to look back for our sensor measurements. For example, in here we have lags set to 5. What that means is we're looking back 5 sensor measurements from the present time step. So in the orange, that's our present time step, and the triangles represent the sensor measurements. So the orange triangle is like the sensor measurement at the present time step, and the 5 blue triangles to the left of it is the lagged sensor measurements that are also being used. So together, the 5 lagged sensor measurements as well as the current sensor measurement, so a total of 6 sensor measurements, are used to reconstruct the present full state space shown in the orange rectangle. And if this sounds confusing or unfamiliar, you can visit some of the earlier videos in this playlist that go more in depth about lags. And another parameter we've talked about is compression. So with compression, we're using randomized singular value decomposition algorithm to efficiently find a lower rank approximation of the full state data. So the main goal here is to reduce the dimensionality of your data set and keep only the most important patterns. The benefit of this is the compressed data takes up much less memory, and SHRED will also be able to train much faster on the compressed data. So if you're working with a large data set that can't fit into memory, or you're working with a large data set and you don't have access to a GPU, you might want to consider compression so that it takes up less memory and can train faster. The last parameter we talked about is mode. So mode has 4 options: reconstruct, predict, forecast, and all. So when you pick the reconstruct option, what it does is it splits your data set using a random split method. So the train, validation, and test data is split randomly throughout your full data set. And using this data, we're able to fit what's called a reconstructor. Now, if you choose the predict mode, what happens is your data set is being split sequentially. So from the start time to where the blue ends is where we have the training data. From where the blue ends to where the yellow ends is the validation data, and the rest is the test data. And as you can see visually, the data is being split sequentially in a temporal manner. So we also have the forecast mode, which is, again, we're doing a sequential split of train validation test, but this time we don't have the lagged sensor measurements as input for the test data. So we want to really forecast what the full state space looks like without having the sensor measurements. So you might ask, how on earth can we do this? So we can do this by training a sensor forecaster. So what this sensor forecaster does is it trains on the lagged sensor measurements, and then it predicts what the next sensor measurement will look like. So it trains on the sensor measurements from t minus lags to t, and will predict the sensor measurement at t plus 1. So this is the sensor forecaster. And to forecast, what happens is you first train the sensor forecaster, and the sensor forecaster does a rolling forecast to predict what the sensor measurements will look like in the future. And using the rolling forecasts, we're able to use the reconstructor to reconstruct what the full state space will look like for the forecasted sensor measurements. And here is a summary of the different data sets that each mode will create. So if you choose the reconstruct mode, only the reconstructor dataset is created. If you choose the predict mode, only the predictor dataset is created. Now if you choose the forecast mode, both the predictor dataset as well as the sensor forecaster dataset is created. And if you choose the all option, all three of these datasets are created. So yeah, hopefully that gives you a better understanding of how to initialize the SHRED Data Manager. Next, we're still on the topic of sensor data processing, but we're going to talk about how to add data sets and sensors. So here we have a sample add method. We have the data, which is the full state space data with time on the first axis. And then we have ID, which is a unique identifier for the data set. We have random sensors, the number of random sensors, stationary sensors, which is the locations of the stationary sensors, and mobile sensors, which is the trajectories or list of trajectories of mobile sensors. So it's very important to get the shape of the data set correct. So right now we're working with spatial temporal data, which has a type of a NumPy-ND array. Now the shape is really important. So what you want is you want the number of time steps to be on the first axis, right? Followed by the spatial dimensions. So as you can see here, T is the temporal dimension. That should be your first axis, and then spatial dimensions, which labeled in X's, will come after. And then you have your random sensors. So this is the number of randomly placed sensors that you want. So it is an integer type, and if you want 3 randomly placed sensors, you can just put 3. For the stationary sensors parameter, this is the sensor coordinate or lists of sensor coordinates you want to use. So this is of type tuple or a list of tuple if you have multiple stationary sensors. Now we have an example here where we have 2 stationary sensors in a 2D spatial field. So we have x0, y0, so that's the location of the first sensor, and x1, y1, the location of the second sensor. Next up, we have mobile sensors. So here we have mobile sensor trajectories, or a list of mobile sensor trajectories. The type of this would be a list of tuples for a single mobile sensor, or a nested list of tuples if you have multiple mobile sensors. Example is 2 mobile sensors, A and B, in a 2D spatial field. So here, our first list is for sensor A. We start with the coordinate at time equals 0, and then we go up till time equals t. And then we append it with another list for sensor B, where we start at time equals 0 and go up till time equals t, where t is the number of time steps in your data set. Hopefully this overview gave you a better understanding of the add method for the manager. I also want to mention briefly about multi-field data sets. So if you're working with data that have coupled fields, so you have different fields that you're measuring, or possibly just couple fields where you're measuring only a single field, you can add additional fields using the same approach that we just talked about. So you can do manager.add and then add your new data from a different field, followed by sensors if there's any. And if you don't have any sensor data from the other fields, you can just leave it as .add data and then the dataset ID. So that's how you can work with multi-field datasets. Next up, we have dataset splitting. Here, we're splitting the dataset into train, validation, and test. The code is a one-liner, so we have the train, validation, test dataset is equal to manager.preprocess. Here's an overview of what a single train dataset would look like. The type is of SHRED dataset, and inside the train dataset, we will have one and up to three time series datasets. So we have the reconstructor dataset, predictor dataset, and sensor forecaster dataset. So however many you have here depends on what mode you selected earlier when you configured the SHRED data manager. And in each time series dataset, you have your typical X and Y, where X is the data input data that goes into SHRED, and Y is the output. And yeah, so there is the train validation test split. Next up, we have model training. So the first step here is to initialize SHRED. So the initialization is pretty simple. You do SHRED, and then the first thing you have is the sequence model, followed by a decoder model. What's cool about PySHRED is it has a modular framework. So what this means is you can select what sequence model you want to use and pair it with the decoder model you want to use. So by default, the default sequence model is the long short-term memory network, and the default decoder model is the shallow decoder network, and that's in the green. However, you can switch it up however you would like. You can mix and match any sequence model with any decoder. For example, you can have an LSTM paired with a UNET decoder, or a transformer paired with a UNET decoder. So this customization is a very cool part of this PySHRED package. There's a lot of presets for the sequence and decoder models, and to use those preset models, you can just input a string. So if you want to use LSTM, just put LSTM. If you want to use SDN, just put SDN. And these preset models work surprisingly well on a large variety of data sets. So I recommend giving the preset options a go first before you customize your own. So if the presets don't work and you want to fine-tune your model, you can customize it by setting, for LSTM, you can customize it by setting the hidden size to what you want, the number of layers to what you want, and then you can also customize the shallow decoder network with the parameters that you want. And you can do this with any sequence or decoder model, and once you've customized it to your liking, you can just input that model into SHRED, just like you did with the strings. The last step in model training is fitting SHRED. So here we have the code shred.fit, which takes in a train dataset, a validation dataset, the batch size, the number of epochs you want to train for, the learning rate, and the patience. So patience is the number of epochs you want to wait where the model doesn't improve before you terminate training early. Once you've trained your model, so you have a fitted SHRED model, you can evaluate it. So here is model evaluation. The default metric used in the package is the relative L2 error. So this is the 2 norm of the difference between the truth and the prediction over the 2 norm of the truth. And for the evaluation results, there are 5 main categories. There's the reconstruction evaluation, prediction, forecast, one-step sensor forecast, and rolling sensor forecast. So there's 5 different evaluations. So for the reconstruction evaluation, what it does is it takes in the reconstructor data set, right? So it looks specifically at the test data in the red, and reconstructs what the full state space looks like in the red time steps and calculates the error from that. In the prediction, it takes in a sequential data set. So here we're passing in the sensor measurements, where in the red, so the last subset of the data set, and then we try to reconstruct it. So this is called prediction, and next we have forecast. So this is the error where we perform a pure forecast. So we don't have the test sensor measurements. Instead, we use our sensor forecaster to forecast these measurements and then predict what the full state would look like. So out of the three between reconstruct, predict, and forecast, typically does the worst, and reconstruct typically does the best. And then for evaluating the sensor forecaster, we have the one-step sensor forecast metric, where we're mapping the lag sensor measurements to the sensor measurement at the next time step. And then we also have a rolling sensor forecast evaluation result, where we're performing basically a rolling forecast, so we don't have any of the test sensor measurements, but we want to forecast all of them. So this is what we mean when we use a rolling forecast. So this will always be worse than the one-step sensor forecast. So for evaluation, you can either evaluate on the raw model output, or you can evaluate on the model output once the output has been uncompressed and unscaled. The benefit of evaluating on the raw model output is the results can be directly compared with the validation error. So if you see the test error is like way worse than the validation error, the data probably overfit on the data set. You can also evaluate on the post-process data. So here you're calculating the evaluation error on unscaled and uncompressed data. So the only difference here is in the evaluate function, you're passing in the model and data set just like before, but this time you're also passing in your data manager, which is used to unscale and uncompress the data. A quick note is the results, the evaluation results here cannot be directly compared with the validation error that's shown during training. This is because the validation is not unscaled and uncompressed. Once you are satisfied with the evaluation results, we can move on to using SHRED to perform various tasks. Here we're doing a reconstruction using our fitted model on test data set. So as you can see in the code here, we have the shred.reconstruct function, and what we're passing in is the test data set for the reconstructor for the input X. And once we obtain the reconstruction from shred.reconstruct, we can pass that reconstruction into manager.postprocess. Along we have to pass the mode. So here we're doing a reconstruct, so we pass the reconstruct mode. So what this does is it unscales and uncompresses the model output so that the shape of the data, the scaling, is back to what it was originally before the data was processed. Now we don't have to just limit ourselves to the test set. We can also reconstruct on really any data we want. And to generate the input data X, we can use manager.generateX. This takes in a start time, an end time, and the mode that you want to use. So typically for the reconstruct mode, the start time and end time would be within your data set, so from 0 to t. And once you generate your sensor measurements, you can again pass it into shred.reconstruct. Next, we also have the predict functionality. So here is an example of using predict on the test data set. So the format is very similar to reconstruction, but instead we have shred.predict, and now we're passing in the X of the predictor data set. And then again, it's followed by post-processing, but this time the mode is set to predict. This makes sure that the unscaling and uncompression that is used is for the prediction data set and not for the reconstruction data set. We can also predict for sensor measurements in general by again using manager.generateX to generate sensor measurements. So in the predict case, what we're doing is we have new sensor measurements, and with these new sensor measurements, we want to generate reconstructions. Now we can do this by passing those new sensor measurements into generateX. Now this generates the lagged sequences that we need to pass into SHRED. So once we get that, we can just do shred.predictX. And finally, we have forecast. So a forecast is really just 2 steps if we break it down. So it forecasts the sensor measurements, and then it makes a prediction based on the forecasted sensor measurements. So to use the forecast, what we do is we use the manager.generateX. Here we put in a start time, an end time, and then we pass in our forecaster, so shred.sensorForecaster, and then mode we'll set to predict. So we're using predict because once we do generate the new sensor measurements that we want, so we generate it using that rolling forecast approach with the SHRED sensor forecaster. So once we do generate that data, we're still using shred.predict function. So that's why the mode is predict. So once we generate X, we can pass that into shred.predict to obtain our full state forecast. So those are the 3 main functionalities of SHRED. And now I want to briefly talk about generateX, which is what we saw earlier, is used to generate the lagged sensor sequences. So for generateX, what it does is it first uses any previously available sensor measurements. So when you passed your data set into the manager, it had measurements that went from 0 to t. So it first checks, okay, for the time steps that you want from start to end, does it include any sensor measurements that's already available to it? So if not, it checks if there's newly available sensor measurements. So this is the sensor measurements that you can pass into generateX, and it checks if those are available. And if those are also not available, the generateX function uses the SHRED sensor forecaster to fill in any of the remaining gaps that aren't covered by either the previously available sensor measurements or the new sensor measurements that you passed into generateX. Next step is to add this data to the SHRED data manager. So we use the manager.add function. For data, we set it to SST data. And then here we're going to use stationary sensors. So I selected 3 random stationary sensors. I set these so that you can follow along and have the same sensor locations as me. Otherwise, you can typically just use random sensors set to 3. And for ID, I called this dataset SST. And once you add a dataset, you'll have a few attributes that you can look at. So here is the manager.sensor summary. So what it is a pandas data frame of sensor information. So it tells you what field it is, what's the sensor ID, what type of sensor. So here it's stationary, and the location or trajectory of the sensors. And with this information, you can plot it on top of your full state space, so you can kind of visualize where these sensors are. So we have the orange, purple, and cyan dot. So these are the 3 sensors that we've added. Another attribute is manager.sensor measurements. So this shows all the sensor measurements that comes from the 3 sensors that we selected. So we can plot that as a time series as shown down below. So it spans from 0 to 1400 weeks. And we have the 3 sensors in 3 different colors. And we can really see the yearly trends as it oscillates back and forth. The next step is to split our data into train validation tests, and that's just a one-liner, manager.preprocess. The next step is to initialize SHRED. Here we'll use the vanilla LSTM to encode the temporal data, and then we'll use a SDM decoder. Next up, we'll fit the SHRED using shred.fit, and then we're going to pass in the train data set and valid data set that we generated earlier. Next, we're going to evaluate our fitted model. So what we're going to use is that evaluate function, pass in our SHRED model, and pass in our test data set. So here is the relative L2 errors for reconstruction, prediction, forecast, one-step sensor forecast, and rolling sensor forecast. What we can see is among reconstruction, prediction, and forecast, the error is smallest for reconstruction, and prediction is slightly lower than forecast. So based on how the data is split and what these modes actually mean, this makes sense. So reconstruction is typically the lowest, prediction is worse, and forecast is typically the worst out of the 3. And then we have the errors for our sensor forecaster. And for rolling forecast, it will always be worse than the one-step sensor forecast. Next, we can evaluate our post-process data. So this is similar, same evaluation, but this time it's evaluating on data after it's been unscaled and uncompressed. So the only difference here is we're adding a data manager and setting that to manager. So here you get the relative L2 errors on the post-process data. You can still see the reconstruction is the best of the 3, prediction is worse, and then forecast is the worst. And of course, the rolling sensor forecast is worse than the one-step sensor forecast. Cool. Now that we've taken a look at the evaluation, we can start using our trained SHRED model. So we can do shred.reconstruct and pass in the test data set to perform a reconstruction on the test data that we have. And after that, we can post-process it so that the data is unscaled and uncompressed back to the original shape before the SVD compression. And here is a visualization of what the post-process data looks like for the reconstructor. So as you can see, the model output looks very similar to the ground truth. So that's a very good sign. Next, we have the predict functionality. So here we're just using shred.predict, and we're passing in the test data set for the predictor. And again, we're doing some post-processing so we can plot what they look like. Here again, we have the model output and the ground truth for predictions, and as you can see, they also look very similar, which is a super good sign. One way we can compare them is plotting a difference plot. And then here is the forecast. So to perform a forecast, what we're going to do is we're going to first forecast the sensor measurements using GenerateX. So our data set went from 0 to 1,399. So those are the time steps that we had. So what I'm going to do is forecast from 1,400 to 1,500. So this is like not part of the data set that we started with. And then I'm going to set the mode to predict, and then forecaster to use shred.sensorForecaster. So this will perform a rolling forecast to generate the new sensor measurements. And once we generate that, we have the X, we can just pass it to shred.predict to generate our forecast, and then post-process it with the mode equal to predict. And boom, here is what our forecast looks like at time step equals 1500. So this is not part of the original data set we worked with, which only went to 1399. And yeah, so that's conclusion. That's a conclusion of the tutorial, as well as a brief overview of what the PySHRED looks like. There will be more tutorials coming soon, coming shortly, and yeah, so quick overview of the PySHRED package. These are its functionalities, and yeah, we'll have more videos on multi-field shred, parametric shred, as well as the other shred variants. And as always, here's the GitHub link where you can find the PySHRED package, and once it's officially released, you will be able to find it on PyPy, and the documentation will also be there. Thank you.